So picture this. You're standing on this breathtaking piece of land, right?
Yeah, overlooking the mountains.
Exactly. You're up in the Highlands Cashiers Plateau of North Carolina. The views are just incredible. You're at this elevation over like 3,500 feet, and you are ready to build your dream mountain home.
Sounds perfect.
It does. But there is a huge catch hiding just, maybe 2 inches below your hiking boots, and it's solid ancient rock.
Right, yeah. And it's not just any rock.
No, it's not. I mean, if you want to build a house up there, the most expensive thing you buy won't be the custom lumber or those massive architectural windows.
Usually not, no.
The biggest line item on your budget is probably going to be the cost of destroying this 300-million-year-old metamorphic armor.
Yeah, that landscape actively resists being altered. It really does.
Which is exactly what we're getting into today. Welcome to the Deep Dive, everyone. Our mission today is to uncover the deep earth science behind the rocks of Western North Carolina and really look at how that geology dictates the modern reality, the costs, and the literal mechanics of building a home there.
It's a fascinating overlap of deep time and, well, modern construction.
Definitely. And to do this, we're combining 3 really cool sources. We've got 2 deep dive geological transcripts that explain metamorphic rock formation. And we're pairing that with some practical insights from Carrie Bateman, who is a realtor and advisor specializing in the Highlands area.
Right. And her insights are so key here because in places like Highlands or Cashiers, Glenville, Sapphire, you really aren't just building on the land.
You're kind of building into it, right?
Exactly. You have to build into the mountain itself. That whole flatlander mindset of, just digging a hole and pouring a foundation.
Scraping away some dirt.
Yeah, that totally goes out the window. Because this mountain is made of some of the hardest, most complex rock on the entire continent.
Okay, so before we can even talk about how builders managed to break this rock, we kind of need to understand why it's so incredibly tough to begin with.
For sure. So the Highlands Cashiers Plateau is essentially built on a foundation of high-grade metamorphic rock, mostly granite, gneiss, and schist.
Okay, assuming we all remember the basic difference between like igneous and sedimentary rock from middle school science, how does metamorphic rock get so dense that it literally dictates an entire regional real estate market?
Well, metamorphism is basically a story of extreme directional stress. We're talking about the historical collision of tectonic plates.
Like the African plates smashing into North America.
Exactly. The exact same forces that built the Appalachian Mountains. So when pre-existing rock gets dragged deep down into the Earth's crust, it gets subjected to just crushing pressure.
Oh, wow.
Yeah, intense heat, and often these injections of superheated ion-rich fluids.
Okay, so I'm trying to visualize this restructuring. It's usually described as a pressure cooker, but I'm picturing something a bit more chaotic.
How?
Like, imagine a crowded room full of people just milling around randomly, taking up space. And suddenly the walls start slowly closing in from 2 opposite sides.
Oh, I see where you're going with this.
Right. So to survive the crush and just take up less space, everyone in the room has to link arms, stand shoulder to shoulder, and organize into these really tight parallel lines.
That is actually a highly accurate way to look at solid-state recrystallization.
Solid state, wait, so it never turns into lava?
No, that's the most mind-rending part of the whole process. The rock never actually melts.
Really? With all that heat?
If it melted into magma, it would just cool back into an igneous rock.
Oh, right.
Instead, the heat gives the atoms inside the solid rock just enough vibrational energy to literally migrate through the crystal lattice.
Through solid stone. That is wild.
They break their old bonds, they shuffle around, and they form entirely new, vastly more stable mineral structures, all without ever turning into a liquid.
Okay, atoms migrating through solid rock to find a more efficient packing shape. That level of density is hard to even wrap your head around.
It really is.
But wait, if it's just a matter of intense pressure, do all rocks down there turn out the exact same?
Yeah.
Why are the rocks in the plateau so famously striped and kind of flaky?
Okay. That is a process called foliation.
Osiation.
Yeah. Foliation happens when the parent rock, the original rock, contains a mix of different minerals, especially flat, platey ones like micas.
Okay, the shiny, flaky stuff.
Right. And when that mix is subjected to that directional pressure we just talked about,
Right.
Well, imagine you have a pile of assorted pens and pencils.
Just scattered randomly on a desk.
Exactly. A totally disorganized pile. Now, put your hands on either side of that pile and slowly push them together.
The pens are going to be forced to line up.
Yep.
I mean, they have no choice but to turn parallel to each other, right? Just to fit into that compressed space.
That is exactly what happens to the microscopic crystals inside gneiss and schist. As the tectonic plates collide, the crystals are forced to align.
So the rock literally grows stripes.
It does. Let's trace it. It might start as a simple mudstone, just compressed clay. Then under pressure, it turns into shale. More pressure, it becomes slate.
Like roof tiles.
Exactly. Even more pressure, you get phyllite. Then schist, which has those really large, scaly mica crystals.
Okay, so schist is pretty far along in the process.
Very far. But under the absolute highest grades of tectonic pressure, before the rock literally melts, it becomes gneiss.
A gneiss. Spelled G-N-E-I-S-S, right?
That's the one. And in gneiss, the conditions are so extreme that the dark and light-colored minerals completely separate from each other.
Oh, so that's why you get those super distinct bands.
Yeah, you get these brilliant, highly visible bands of light quartz and feldspar alternating with dark micas.
I mean, visually it sounds beautiful. But structurally, I imagine all those layers and complex structures create just absolute nightmare scenarios for a builder.
Oh, they absolutely do, especially when you introduce anomalies into the mix. Things like porphyroblasts.
Porphyroblast. That sounds like a sci-fi weapon.
That sounds like it, yeah. But it basically just means that while the rock is metamorphosing and those atoms are shuffling around, sometimes entirely new, abnormally large crystals just spontaneously grow right out of the solid mass.
Like what kind of crystals?
Well, in the schist found around the Highlands Plateau, these are very often garnets.
Garnets, like the gemstones. You just have semi-precious stones embedded in the bedrock.
Exactly. Which, is geologically fascinating, but practically, it is brutal for construction.
I can imagine.
Picture this. You're an excavation contractor. You're running a massive multi-$1,000 tungsten carbide drill bit into what looks like relatively uniform schist.
Okay.
And suddenly your drill bit hits a concentrated pocket of garnets.
And garnets are super hard, right?
Significantly harder than the surrounding rock.
So the drill bit just, shatters?
It shatters. The equipment breaks down, your timeline completely stalls out, and your budget takes a massive hit.
Wow. So the microscopic atomic structure of a rock formed millions of years ago is directly impacting the daily, literal mechanical reality of a modern construction crew.
It dictates everything they do.
Which brings us to the actual terrain itself. Because if this high-grade metamorphic rock is so unyielding, what does that mean for the topsoil? I mean, I imagine millions of years of weather haven't really made much of a dent in it.
You'd be right. The topsoil on the plateau is incredibly shallow.
How shallow are we talking?
Well, in flat, coastal, or Midwestern regions, builders can often dig down 10, maybe 15 feet and just hit more dirt or clay.
Right, easy digging.
But up in Highlands, when you try to cut a driveway into a slope or prepare foundation or even just dig a narrow trench for a water line, you are going to hit solid, gneiss, or schist almost immediately.
Okay, let's unpack this for a second.
Yeah.
Because if I'm a buyer and I'm walking a mountain lot and I see a bunch of exposed natural rock ledges and stone just breaking right through the thin dirt, my instinct is to run away. I'd think, why buy a property where I have to wage a geological war just to pour a foundation? Shouldn't I just go find a nice, flat, boring spot of dirt?
It's a natural instinct. But dirt on a steep mountain slope is essentially just a landslide waiting to happen.
Oh, well, that's terrifying.
Right. And this is where Carrie Bateman's real estate advisory insights become so critical for buyers looking in that area.
Because she deals with this every day.
Exactly. She points out that the required perspective shift for a buyer is realizing that visible rock is not a defect. It's actually an indicator of structural stability.
Ah, okay. Because you want your house attached to something that hasn't moved in 300 million years.
Precisely. I mean, think about the engineering required to build on a really steep grade.
I guess if you're building on deep soil, you're constantly fighting gravity.
You're fighting erosion, water runoff, and just the sheer weight of the house shifting the earth over time. But when you have high-grade gneiss right at the surface, structural engineers can drill heavy steel dowels and micropiles directly into the bedrock.
Oh, wow. So they literally pin the house to the mountain.
They pin it right to the Earth's crust. It offers unparalleled long-term durability.
You know, Carrie Bateman actually had a really striking quote about this dynamic in the source material. She said, "The land is not simply where a home is placed. It determines how that home can exist."
It's a perfect summary. The mountain dictates the architecture.
So you're not just flattening it out.
No, you rarely see someone blast a massive, flat, suburban-style pad into the mountain. The most desirable properties, the ones with those jaw-dropping views and deep privacy, they're almost always on steep terrain.
We're dealing with the rock is just a mandatory part of the design process.
Right. You design a home that steps down the topography, and you utilize the rock as part of the structural and even aesthetic plan.
Okay, so we've established the rock is inevitable, and it's actually structurally beneficial. But the next logical question is, how do builders actually move something that took shifting tectonic plates millions of years to forge?
That is the big question.
Mm.
And the methods used to break high-grade metamorphic rock are highly specialized.
Because when most of us hear the phrase rock blasting, I think we all picture the exact same thing.
A chaotic, cartoonish explosion.
Yeah, the Wile E. Coyote approach, just pushing down a TNT plunger and sending boulders into the stratosphere.
Right. But the reality of modern rock blasting, especially in heavily regulated, environmentally sensitive areas like the plateau, is entirely different.
I would hope so, for the neighbors' sake.
It is a highly controlled, tightly engineered civil engineering tactic. The goal is to fracture the rock in place, not to launch it into the air.
But how do they control explosive energy like that?
Well, they actually use the rock's own internal structure against it.
Oh, the foliation. The stripes we talked about?
Exactly. Blasting crews will map out the site, and they drill a very specific pattern of holes based on those foliation planes.
Okay.
Then they calculate the exact minimum amount of explosive force needed to break the bonds along those specific planes.
So they aren't just packing it with as much dynamite as possible.
Not at all. And here's the clever part. They load the holes with the charge, but then they do something called stemming.
Stemming, what's that?
They pack the top of the hole above the explosive with crushed stone.
Oh, I get it. So when the charge goes off, the rapidly expanding gases can't escape straight upward out of the hole.
Exactly. The energy is forced horizontally into the surrounding bedrock, cracking it apart internally.
It's basically a localized, suppressed release of energy.
Very localized. And crucially, this entire process is monitored by seismographs.
Wait, like earthquake sensors?
The exact same technology. They place acoustic and vibration sensors all around the perimeter of the construction site.
I assume that's primarily for liability, like protecting the neighbors from claiming you cracked their driveway.
Liability is a huge part of it, yes. It provides hard, documented data. If there's a neighboring home nearby or maybe a really delicate retaining wall downslope, the seismograph proves that the peak particle velocity, which is the actual vibration moving through the ground, stayed well below the threshold that could cause structural damage.
That's amazing.
Mhm.
It takes this terrifying concept of blowing up a mountain and turns it into a predictable, mathematically managed process.
It's all just math and geology.
But there have to be situations where you absolutely cannot use explosives, right?
Yeah.
I mean, what if the rock load you need to remove is like 3 feet away from a newly poured concrete foundation or right next to a giant pane of custom architectural glass?
You're totally right. Blasting isn't always an option. And that is where alternative technologies come in. Specifically, the use of expansive agents.
Expansive agents, like a chemical.
Yes. Builders will drill that same precise pattern of holes, but instead of loading them with explosives, they pour in a specialized chemical slurry.
What's in the slurry?
It's usually a highly engineered bentonite clay compound.
Okay, wait. I think I know where this is going. Is it essentially the same mechanism as when water freezes in a pipe during the winter?
How do you mean?
Like the water turns to ice, it expands, and it splits the solid metal pipe right open from the inside out.
It is the exact same physical principle.
That's brilliant.
As this bentonite clay compound hydrates, it undergoes a chemical reaction. It generates heat, and it causes the material to crystallize and expand.
And it cracks the rock.
Yep. But it's not instant. Over
Yeah.
the course of, say, 24 to 48 hours, it just exerts thousands of pounds of pressure per square inch.
So you're basically doing the ice pipe thing on purpose with special clay to quietly split a mountain apart.
Silently and slowly pushing the rock apart from the inside. It cracks the bedrock into these manageable blocks that an excavator can then just lift away.
Zero noise, zero vibrations, zero flying debris. It's like geological judo.
Geological judo, I like that. It allows for incredibly surgical excavation in highly sensitive areas.
But, as you pointed out, it takes 24 to 48 hours. It requires days rather than seconds.
And that brings us directly to the logistical reality of building here, time and money.
Let's talk about the bottom line.
Mm-hmm.
Because the physical mechanics of this drilling through bedrock, shattering expensive drill bits on garnets, bringing in seismograph crews, or waiting 2 days for clay to expand, all of that sounds incredibly, incredibly expensive.
It is a significant line item, but the presence of high-grade rock doesn't automatically mean a project is doomed to endless delays or a blown budget.
It doesn't.
No. What it introduces to the schedule is a high degree of variability. Builders and cashiers and Highlands, they just expect to hit rock. It's a given.
Right.
So they build buffer time into the early phases of the schedule because, frankly, you simply cannot x-ray the mountain before you buy it.
But wait, you can do core drilling and soil borings during your due diligence period.
You can, and you absolutely should. Carrie Bateman would certainly advise you to do that. But a core sample is just a tiny, localized snapshot of the ground until the heavy equipment actually starts stripping back the shallow topsoil across the entire footprint of the home and the driveway. You really cannot confirm the total volume of high-grade gneiss hiding underground.
Okay, so what are the actual cost drivers when you finally do uncover that rock? Like, if I'm looking at a site prep bill from my builder, what makes one lot cost vastly more to clear than another?
Well, there are 4 primary factors driving excavation costs in the plateau.
Okay, what's the first one?
The first is straightforward, the sheer volume of the rock.
Makes sense.
Right. Chipping out a few cubic yards for a footer, that's a minor line item. But excavating an entire lower-level walkout basement into a solid wall of gneiss, that is a major engineering event.
Yeah, that sounds like a massive undertaking. And the second factor has to be the terrain itself, right?
Absolutely. Slope and accessibility. The steeper the lot, the more dangerous it is to position the drilling rigs and the heavy excavators.
I didn't even think about just getting the machines up there.
Oh, it's a huge deal. You have to physically get massive equipment up a winding, narrow, 15% grade mountain switchback.
That sounds terrifying.
Sometimes, just the logistics of delivering an excavator to the site costs a premium before the machine even turns on.
Okay, so we have volume and we have slope access. What's the fourth factor?
Well, the fourth factor is the one buyers almost always fail to account for: hauling.
Hauling the rock away.
Yes. Once you blow the rock up or crack it apart with that expansive clay, you are left with tons of heavy, jagged rubble.
And you can't exactly just leave a mountain of fractured gneiss sitting in your new front yard.
Right. And you can't just throw it in the back of a pickup truck either.
No.
This is where the physics of excavation really hits the wall at the hardest. When you crack a cubic yard of solid, dense, metamorphic rock out of the earth, it essentially fluffs.
Fluffs. Like a pillow.
Well, it loses its compact puzzle piece structure. While it was in the ground, it was perfectly solid, but once it's broken, those jagged edges don't fit perfectly together anymore.
Ah, I see. Because you've introduced empty space between the fragments.
Exactly. This is known in the industry as the swell factor.
The 12 factor.
Yeah. Fractured rock actually takes up to 30 to 40% more space in a truck bed than it did when it was sitting in the ground.
Wait, 40%?
Up to 40%, yes.
So hold on. You aren't just paying to move the rock you dug out. You're actually paying to haul the newly introduced air between the rubble.
You are literally paying to haul air.
That is insane.
It requires more dump trucks, more trips down the mountain to a disposal site, vastly more diesel fuel, and exponentially more hourly labor.
I mean, if the disposal site is an hour away, you are paying a fleet of drivers to transport 40% empty space down a treacherous mountain road.
That's the reality of it.
That paints a completely different picture of site prep costs.
Which is exactly why we bring this back to the core philosophy advocated by experts like Carrie Bateman. When prospective buyers walk onto a piece of land in the Highlands Cashiers area, their first question is almost always, does this property have rock?
But knowing what we know now about the African and North American tectonic plates colliding to form this whole region, the answer is always yes.
Always.
It's armor all the way down.
Exactly. So the question shouldn't be if there is rock. The vital question a buyer must ask is, how should this property be built?
Right. It's about shifting away from a mindset of fighting the terrain and moving toward a mindset of architectural integration.
That's the key. The most successful buyers, they evaluate the topography before they ever close on the land.
They don't just look at the view.
No, they bring in experienced mountain builders and site specialists during the due diligence period. They don't just look at the sticker price of the acreage either. They actively calculate the total site costs.
Because a cheaper lot with brutal rock excavation and terrible hauling access could actually cost significantly more overall than a premium price lot that has natural manageable slopes.
Exactly. And site prep shouldn't be viewed as a penalty either.
No,
Think of it as an investment in the foundational integrity of the home.
that makes a lot of sense. The rock, the elevation, the steep terrain, those are the defining characteristics of the plateau. They're the literal reasons people want to live there in the first place.
Right. And with proper due diligence and engineering, the geology becomes the greatest asset of the property, rather than some catastrophic surprise that destroys your budget.
Man, this whole journey from microscopic clay minerals, settling in ancient oceans, getting squeezed into beautifully banded gneiss, and eventually being mapped by seismographs and shaped by expanding clay, it's just incredible.
It really is.
It fundamentally changes how you view the ground you're standing on.
It certainly elevates a standard real estate transaction into a much, much grander geological context.
It totally does. And, to wrap up today's deep dive, I just want to leave you with a final thought to mull over.
Okay, let's hear it.
Well, we are incredibly accustomed to viewing houses as temporary, almost consumable structures, right?
Sure. We buy them, we remodel them every 20 years.
Exactly. The materials degrade, styles change, and eventually the home is just torn down to make way for something new.
The human architectural timeline is exceptionally brief compared to the landscape.
Right. But if you go through this monumental process, if your custom engineered home is literally bolted and pinned deep into a bed of metamorphic that took hundreds of millions of years to forge,
Yeah.
how might that deep geological permanence change the way we think about the legacy of the homes we build? I mean, if the foundation is essentially eternal, what does that demand of the architecture, the craftsmanship, and the lifespan of the structure we place on top of it?
That is a fascinating perspective, building for the ages, literally.
It's definitely something to think about the next time you see a jagged piece of rock breaking through the soil on a mountainside.
Absolutely.
Well, thanks for exploring this with us, everyone. We'll catch you on the next deep dive.